So the previous lecture video looked at the measure of spread called the range, which only used two observations to come up with its measure of spread. In this video, we're going to learn about the measure of spread called the standard deviation and the variance. And these two measures of spread use every single observation to come up with its measure. The standard deviation, what it is it measures on average how far is an observation from the mean. So you'll find the mean of a set of data, see how far each observation is from the mean, and then take the average distance. Now, there's two different notational pieces for the standard deviation. Sigma denotes the standard deviation, or the average distance an observation is from the mean, for an entire population. S represents the standard deviation of a sample, which denotes the average distance an observation is from the mean for a sample of data. The variance, on the other hand, essentially does the same exact thing as the standard deviation, except that it measures the average squared distance an observation is from the mean. Not the regular distance, but the squared distance. And you'll notice the notational pieces for the variance are similar to that of the standard deviation. Sigma squared to represent the variance of a population, and S squared to represent the variance of a sample. This is because the variance measures the average squared distance or deviation from the mean, compared to the standard deviation, which measures the average distance an observation is from the mean. So that's why you'll see that little squared next to the notation for the variance. So I think the best way to represent this concept is to do an example. Here is an example on how to find the standard deviation and the variance for a set of data. So this set of data consists of 5 observations, 5, 2, 1, 9, and 3. And let's assume to start that these 5 observations are our whole entire population. We're only interested in those 5 observations. So if we were to find the standard deviation or the variance, we're finding the average distance or the average squared distance an observation is from the mean. So if we were to do this out for us, the mean, in this case for our population, we would add up these 5 observations and then divide by the total number of them. And if we were to do this out, we would find our mean equals 4. I'm going to draw a nice little line to represent our mean of 4. Now, what we'll do is we'll see, okay, how far is each observation from the mean? And so I'm going to make these nice little kind of distances to visually show you what this looks like. Oops. Right, we're finding how far each observation is from the mean. So in the first case, right, we're seeing how far is 1 from 4. So we're going to look at the distance 1 minus 4, our mean. And that would be our first distance. How far is 1 from 4? We're going to find how far our next observation, 2, is from 4. So we're going to look at how far is 2 from 4. Right? And we'll do this for every single observation in our data set. We're going to see how far is each observation from the mean. And what we're going to do now is we don't just want to find how far each observation is from the mean. We want to find the average distance an observation is from the mean. So what we'll do is we'll take all of these distances, we'll add them up, and we'll divide by the total number of them. We're finding the average distance an observation is from the mean. But we'll notice if we do this out, if you were to calculate this out, this would come out to be 0 over 5, which equals 0. Regardless of how many observations we had, regardless of what those observations are, Every single time you do this, find the average distance an observation is from the mean. Find how far each observation is from the mean. It will always sum to 0, and the average distance will equal 0. This is not giving us a useful measure of spread. If every single time we do this, we get 0. So what we need to do is find a way to counteract this. So there's two different ways we can go about this. One of which is take the absolute value of your distances. Just instead of being negative, make it a positive. And to be honest, this seems to be the most logical approach. However, in statistics, a much more used method in order for this to not sum to 0 and equal 0 is not for us to look at the absolute value, but rather to look at the squared distances. We're going to square these distances instead of taking the absolute value. And there's reasons for that. One, as you get more advanced in statistics, it's a lot easier to work with squared distances as opposed to absolute value distances. On top of that, there's some properties that come about from squaring these distances rather than looking at the absolute value. Now, some of these reasons are above an intro stats course, but there are metrics that do use the absolute value distance. So it's not that we don't use it, but there are some benefits and many benefits that come about from squaring it as opposed to taking the absolute value. So now, if we were to do this out, if we were to sum up all of these squared distances, we have 1 minus 4 squared becomes 9. We have 2 minus 4 squared becomes 4. We have 3 minus 1 squared becomes 1. We have 5 minus 4 squared becomes 1. And we have 9 minus 4 squared, which becomes 25. And we'll sum up these squared distances, and then we'll divide by the total number of them. And if we were to do this out, we should end up with 40 over 5, which becomes 8. What we just found is what's called our variance. And we denote the variance as sigma squared. And again, this is the variance for a population. What this measures, what this 8 measures, is it measures the average square distance an observation is from your mean. On average, how far is an observation from your mean, but we're looking at the squared distance as opposed to the regular distance. If we wanted to just find the regular distance of how far an observation is from the mean, then what we would do is say, well, okay, let's undo this squaring. To find the standard deviation, the average distance, what we'll do is we'll take the square root of our standard deviation. And if we were to do this out, we end up with the value, or I should say approximately, not the exact value, we approximately end up with the value 2.83. And we denote this as sigma. We undid the squaring of the variance. So 2.83 measures the average distance an observation is from the mean. 8 measures the average squared distance an observation is from the mean. So what we just found is the variance and standard deviation of a population. And if we were to write these formulas out, we have the variance sigma squared. What we would write this as is we summed up all of the observations from 1 to n, and we saw how far each observation was from the mean, and we looked at that square distance, and then we divided by the total number of observations. For our standard deviation, we did the same exact thing. We summed up all of our observations from the first to our last. We saw how far each observation was from the mean. We looked at that squared distance and divided by the total number of observations, except this time we wanted to undo the squaring. We wouldn't want to find the average square distance. We wanted to find the average distance. So we divided by, or we took the square root of that quantity. So it's the same formula except one has a square root and one doesn't. Now everything we did right here seems logical. We were finding the variance and standard deviation of a population of data. Now what we're going to do is seem slightly strange, but I'll talk a little bit why this is. So imagine instead of finding the variance of a population, imagine instead we wanted to find the variance of a sample. So imagine this instead was a sample of data. These 5 observations are just a small subset of a larger population. Well, a few things we need to change notationally. Number 1, we need to change mu needs to become x bar, because now this is a mean of a sample and not the mean of a population. So I'll change this as x bar as well. What happens when we find the standard deviation and the variance of a population? It seems odd, but what we do is we don't divide by the number of observations. Instead, what we're going to do is everything stays exactly the same, but we're actually going to divide by the number of observations minus 1. So what we should have done instead is divide by the number of observations in your data set minus 1. And that seems very strange, right? I'm going to kind of change these formulas up slightly. Maybe I'll change them all up together. But when you find the variance and the standard deviation of a sample, which we denote as s squared and we denote as s, you divide by the number of observations minus 1 instead of just the number of observations. So if I was to write your standard deviation formula and variance formula for a sample, it's very similar, except now we sum up all of our observations. There's no square root here, right? We're finding the variance. We're summing up all of our observations, but this time we're subtracting from the mean of our sample. We're looking at those square distances, and now we're dividing by the number of observations in our sample minus 1. And that seems wrong. That seems weird. Why would you divide by the number of observations minus 1? It seems like we're making a mistake. The standard deviation of a sample also does that, except this time everything is just under the square root, right? We sum up all of our observations from our first to our last. We find how far each observation is from the mean, in this case the mean of our sample, and we divide by the total number of observations. To make this kind of more clear, I just want to make sure everyone understands everything is under the square root. Everything is under the square root. Now this represents the variance and standard deviation of a sample. So what we should have done, and again it seems odd, is we should have divided this quantity by 4, and we would end up with a variance of 10. And our new standard deviation comes out to be the square root of 10, which is about 3.16. What we're trying to do here is we're trying to use a sample standard deviation or a sample variance to try to make an inference on the population variance or the population standard deviation. And it turns out that when you subtract the amount of observations by 1, you get a better estimate of the population variance or population standard deviation. Now, it's hard to get into the specifics of why exactly that is. However, I'll have a little optional video if you're interested in why we divide by n-1 for the sample standard deviation and sample variance.